All right, we are rapidly approaching the midterm-ish times, right? Good deal. So we're getting there. Yeah, it's about more like 3 weeks.
It's like right before fall break.
Mm-hmm. It is. The Monday and Wednesday before fall break.
Are we split up into 2 sections, or is it just?
Yep, I'll have 2 parts, each of them, one Monday, one Wednesday. The easy questions are on Monday. Easy and medium questions, I should say. The hard questions will be Wednesday. Each time will cover the full gamut of chapters 0 through 13. Okay, so where did we stop off on this? Okay, I think somewhere in the primary standard. Make sure you understand a primary standard, okay? So a standardization, that's going to be where you take a titrant and you standardize it against a primary standard, all right? A primary standard needs to be something that's extremely pure, that you can measure in a very accurate manner, typically through mass calculations. So you'd weigh it out and then do the stoichiometry to figure out how many moles you have, right? And it needs to be something that you can easily get to a state where it is extremely high purity and you can weigh it out easily. Now, what does that mean? Well, let's do an example. The easiest way to figure out primary standards is to understand where things go wrong, okay? Sort of like when you look at a box, the easiest way to figure it out is to look at where it doesn't occupy, right? Or any shape, really. So when you're talking about a primary standard, it needs to be extremely high purity. What would be examples of things that are not high purity? Well, like tap water would not be a good primary standard, right? It would be all over the place. You never know what it's actually composed of, okay? There's other things like that. There's many, many chemicals that are very difficult to get high purity, specifically things that absorb water, like hygroscopic materials. Not only do they have a problem where their weight's changing because they're exposed to the atmosphere, which is the next thing down here, but you also have a problem with you never know what they're absorbing for a fact. Another thing would be like, you know, the charcoal that they use for like absorbing materials out of the air. That's extremely hard to get high purity because it's literally absorbing everything out of the air all the time, right? You're never going to be sure what's in it. And so that's a big issue. Also, there's many compounds that are very difficult to get high purity, okay? They just tend to bind to stuff, and you can't get rid of it easily, but you're never sure exactly what it is, right? They should not decompose under ordinary storage. Typically, you want them to be shelf stable, and you don't want them to significantly decompose over the course of, say, 5 to 10 years, okay? There are many, many, many compounds. If you go to the shelf, you'll notice a very obvious difference between the new samples and the old ones in this labs, right? Have you guys ever just looked? No? Okay. Like, sometime check it out. It's pretty obvious. You've noticed this example, like, in your kitchen, though, right? Like butter. Butter is a great example, right? It'd be a terrible primary standard because it's not shelf stable. It turns into rubber pretty quickly. It should be stable when dried by heat or vacuum. It really can be either that you dry it with, heat or vacuum. Heat's easier though. So it's preferable if it's stable under heat, okay? Of course, you know, that's not unlimited. You can't just crank it up to whatever temperature you want. But you should be able to crank it up to a temperature you could dry it at, right? Like 110, 120 degrees Celsius. So you don't have to wait a decade to dry it, right? Or a year to dry it. That'd be ridiculous. Drying is typically required to remove traces of water absorbed from the atmosphere. This is true of pretty much every primary standard. The only primary standard this won't be true is very, very pure water. Honestly, you should try a primary standard and keep it in a desiccator if you're going to be, don't want to dry it over and over. Okay. A lot of people actually just leave their primary standards in a turned on oven that they dry it in, and they literally just cool it down in the desiccator when they want to use it. That's it. They literally just dry it all the time, forever. But those are ones that have a fairly high usage. You don't want to leave your primary standard at high heat for 2 years. It would increase the breakdown of it. The stoichiometry of the reaction with the titrant is known. If you don't know the stoichiometry, you would be multiples off every time you try to use it, right?
So you were using water as a primary standard.
Water is not typically a primary standard.
Okay, yeah, so I was just asking when it said it should be stable when dried by heat or vacuum.
Well, you don't have to dry water. Yeah, you don't have to. That's why I was saying it's the only one I can think of that would be you never have to dry it. That'd be the only exception. And actually, water can be used as a primary standard, very pure water, or as a primary standard for conductance. So there are tests you could use very pure water as the primary standard. Water also can be used as temperature standards. It can also be used as a density standard. But again, you wouldn't have to, that's the only case you would not have to dry it because it is water, right? Every other case you have to dry it somehow, right? An example of not a good primary standard will be something like caffeine, where, yeah, you could try to dry it, but it also sublimate at the same time, wouldn't it? And so you lose your damn sample every time you try to dry it. That would be a terrible primary standard, right? Absolutely awful. The stoichiometry of the reaction with the titrant is known. This is incredibly vital, okay? If you don't understand your primary standard, it is not a primary standard. All right? Because you can't standardize anything off of it, right? Okay, this is an example calculation. So the calcium content of urine can be determined by this following procedure. Step 1, you precipitate calcium with oxalate in a basic solution. This is the reaction right here. Then step 2, you'd wash the precipitate with ice cold water to remove free oxalate. Then dissolve the solid in acid, which would obtain your calcium. And of course the H2C2O4, the oxalate would go back to the acid, right? And that would be in your solution. That's why you're using the... So then next, you'd heat the solution to 60 degrees Celsius and titrate the oxalate with standardized potassium permanganate until the purple endpoint of reaction 7.1. That'd be your reaction has a purple endpoint, is observed. So let's consider this standardization. Suppose that 0.3562 grams of the sodium oxalate is dissolved in 250 milliliters of volumetric flask. If 10 milliliters of this solution require 48.36 milliliters of potassium permanganate, which is the solution for titration, remember? That's what you're titrating with. What is the molarity of the permanganate solution? So first thing, concentration of the oxalate solution needs to be figured out, right? And so we have a number of grams here. Well, grams is directly related to moles, right? By the molar mass. So we calculate the molar mass. You can do it from the periodic table, but normally you would have looked it up and written in your notebook, this lab, right? So you would then use that. That would give you moles, right? You'll then take the moles and you'll divide it by the volume. You can do this in molarity, or you can do it in millimole. Just make sure you can convert it to whatever your answer should be, right? So if you put milliliters down here, that would be millimole, right? You don't want to do it in? And yeah, anyways, you got the idea. So here we have the number in molarity. We use 0.25, which is 250 milliliters in liters. Okay, so the moles that would be this the oxalate in 10 milliliters would be the concentration in molarity times that volume, right? 10 milliliters. In this case, in liters, because we did in molarity, right? Which would be this. That would give you moles. I find this funny that this is directly from your book, that they did it in molarity here, and then they had to go back to millimole, when they could have just started at millimole, right? But anyways, all you would have had to do was use molarity, milliliters down here to get into millimole. Whatever, let's just add an extra couple steps there. So, we got our millimole, right? Well, the reason we want it in millimole is it's going to make our lives easier in terms of all the other calculations. All right, so our reaction 7.1 tells us that 2 moles of permanganate would react 5 moles of oxalate. So the permanganate must have been, well, it would be moles of your permanganate. There are 2 moles of permanganate for every 5 moles reacted of the oxalate, times the moles that we started with, right? So that moles of oxalate cancel. We plug those in, and we get this number of millimoles. Please note that these moles technically cancel. That's a ratio. That would be a millimole ratio as well. Same thing. So we can plug millimoles in here. Okay. You're all comfortable with me just switching back and forth between moles and millimoles now? Okay, go. Because I'm going to do a lot. Because there's not really any reason not to. All right, so anyways, this gives us this number of millimoles for the potassium permanganate. Of course, the concentration then would be millimoles per milliliter, right? And so we plug in our millimoles. We take our milliliters number that we got up here, plug that in, and we would get a molarity. Very good. Any questions? You're all comfortable with me just going back and forth, millimoles, molarity. You don't need any explanations, right? Because if you divide it by milliliters, the milli cancels.
Where do you find that it's 2 moles of permanganate and 5 moles of oxalate?
That's actually needs your book to do.
Okay.
Yeah, that's that reaction 7.1 in your book.
So, yeah, so
That is not this reaction. No. Yeah. That's actually the calcium oxalate one. Okay. You good with titration calculations? I think, frankly, that you guys have actually had quite a bit of experience with that so far. If you have issues with it, let me know, though, and I'll do some more examples. So keep in mind that you can use titrations in many, many different ways, right? You can use it with an indicator to change color. You can use it with precipitations. You can really anything that you can observe somehow, whether it's an electric probe, whether it's spectroscopy, whether it's a color change, whether it's a precipitation, whether it would be, I guess you could technically try to do it with smell, but that would be very difficult. Anyways, any change that can happen suddenly will work for a titration, right? And so, for example, here's a precipitation one. And our titrant is going to be silver, Our analyte's going to be iodide. Notice it's very similar to what we're going to be doing in the lab. Did you guys see that? You're using silver and chloride there. This is silver iodide. You're using the precipitation to show you if you have chloride, right? Yeah. So it's like a sloppy titration, really. In a gravimetric analysis, we could measure an unknown concentration of iodide by adding excess silver and then weighing our silver iodide. And this is actually one of the nice things about titrations using a precipitate, is you can actually just put excess in and get a solid. So it's very nice. In a precipitation titration, we're going to monitor the course of the reaction between the ionolite and the titrant. This is going to be used to locate the equivalence point at which there's exactly enough titrant for the stoichiometric reaction with the analyte. Knowing how much titrant was added is going to tell us how much analyte was present. The concentration of analyte is controlled by the equilibrium that will exist between the solid precipitate and its ions. So keep in mind the KSP controls this, right? Indirectly, because you have the coefficients. These things are to powers. In this case, they're 1 to 1, but so there is something interesting about this, and that is that if something has a very small KSP, you would expect it to be very, very fast in the titration, right? It's going to fall out really fast. But if something has a small KSP, or God forbid, a positive KSP, this is not going to precipitate quickly, right? This is going to stay in solution very well. So these are precipitation titration curves. They look a lot like all other titration curves because they are titration curves. Keep in mind though, precipitation titration curves are not always 1-to-1 ratios. Okay? This is the big difference between acid-base ones and precipitation ones. So in an acid-base one, you protonate everything first with 1 proton, and if it's polyprotic, you do it again, right? And so you essentially just get 2 titration curves stacked on top of each other. In a precipitation titration curve, you have to completely protonate each thing. Or, you know what I'm saying. You have to put cations into each anion. You can't just put one on all of them. That won't cause a precipitation, right? Does that make sense? Okay. So you don't get that stacked. Like if you have an Mg, which is a 2+, MgCl, you need 2 chlorines on there to get a single precipitation. You can't just put one and it'll be okay. It's not going to precipitate. So before the equivalence point, you're going to have excess analyte. The concentration will equal the fraction remaining times the original concentration times the dilution factor. This is actually the part that people forget the most, is you're diluting it each time you put something in, right? So every time you put a drop in, you dilute it more. Okay? So you gotta do a concentration calculation every time. The concentration of the titrant can be found from the solubility product, the KSP, of the precipitation, and the known concentration of excess analytes. At the equivalence point, the concentrations of both reactants are governed by the solubility product, the KSP. That will tell you how high that equivalence point is going to be. Okay? After the equivalence point, you are just adding excess titrant. Again, this is going to be the solubility product. Right here we see an example. So here we have, remember we always do this in P of, negative log of, because this is a logarithmic scale, and it would be very difficult to look at if it's not the negative log of, okay? So it's always P of an ion, in this case P of Ag. This is the volume of your titrant in milliliters. So you see at first, you have very little silver in your system because you're adding silver as your titrant, right? And you see at first, this silver doesn't go up, doesn't increase in concentration quickly, does it? Why is this? Well, it's getting used up by the iodide, right? It's forming the precipitate and falling out. Okay? So once you've used up all of your iodide, what's going to happen? So when you get close to using it up, all of a sudden your silver starts spiking heavily, doesn't it? And when you use it all up, it spikes essentially straight up and down because you don't have any more iodide to use up your silver, right? And that's what you're looking for, is your equivalence point. You will never see a nice behavior like this where it has the a point in the middle, right where your equivalence point should be. This is obviously fake data, right? Or somebody did this knowing what the PAG would be, right? You'll never get that in real data. And again, this is a titration curve. You always plot the P negative log of whatever you're looking at. So whatever you know the concentration of, versus the volume of the titrant right here. The high values, px, this is going to be very low concentrations because it's that opposite, the negative log, right? And these are factor 10 changes in concentration. Okay? Anybody have any questions about that? Is that revving your memories? Are you remembering? All right, so what happens if we have a larger amount of iodide? Well, that's going to cause this curve right here to lower, or go up, excuse me, because less concentration, right? The iodide will use up more of the silver. The equivalence point will still be the same because at the higher concentrations of iodide, you're going to go at a lower point here. And so you get the same equivalence point. Doesn't change. Note this is where you have excess iodide. This region you'll have excess silver. So you keep just adding it, right? What determines how low this gets right here, by the way? If this low, how low this gets, is literally just the concentration of your titrant. It'll approach the concentration of your titrant without ever reaching it. Okay? So let's calculate PAG when 0.1 molarity AgNO3, which is how you typically deliver silver, because that's one of the few places it's highly soluble, AgNO3, is titrated with 25 milliliters of 0.05 molarity after the following additions of AgNO3 titrant. So at VE, 10 milliliters, 40 milliliters of AgNO3 is added. So let's look at VE. We have to first find that VE. The moles of the silver nitrate will equal the moles of the iodide. So we're going to have the VE, the volume at equilibrium. Everybody's okay with VE? Volume at equilibrium. Times 0.05 millimoles per milliliters. So we'll have 25 milliliters times 0.1 millimoles per milliliter. That would give us our 0.05, excuse me. That would give us 50 milliliters for our VE. which is what we see there. Is that okay? Milliliters for our volume at equilibrium. So at the equivalence point, all of the iodide has precipitated as AgI, and the only source of iodide in Ag plus is from that KSP equilibrium. And so that's literally your equilibrium position, right? Which would give you equivalence. All right, now, I should say that this is not necessarily, it is an equilibrium that is established, but the equivalence point is where these are equivalent, okay? Note there's many different equilibrium points. They're all based on KSP, right? And they feed back and forth between the two concentrations through KSP. Does that make sense? Like, you don't have to have the exact same concentrations for all equilibrium points, right? You guys understand that okay? All right, it's sort of a misunderstanding. What do we got here? KSP, we have a KSP value. That's the KSP expression. Note at KSP, the Ag does not have to equal iodide normally, but because we're equivalence point, that is true, right? That is the equivalence point. So because we're at the equivalence point in this case, we know this, that the silver has to be stoichiometrically equal, in this case 1-to-1, right, with the iodide. And so we can have a simplification of this. Well, whatever concentration of iodide we have at the equivalence point has to be the same as silver, right? And so we can plug in KSP equals the silver concentration squared at the equivalence point, okay? Note that is not because of equilibrium, okay? That's one thing that people get confused on. All right, so how do we solve? Well, we solve by going Ag plus and then the square root of KSP. Notice we're just on doing the square here. That would also equal the iodide concentration, by the way. So we square root this value of KSP that we would get from a book. And we get this concentration right here, which is 3.8 times 10 to the negative 8th molarity. That would be your concentration of silver and iodide at your equivalence point. If we take the negative log of that, that would give us our PAG, which is 7.42, which is right there. Notice that is the middle of that. See that? So if you were to go 50 and then plot over, you'd find that to be 7.42. Anybody have any questions? No? Okay. And yes, this positions here, except for this last position, are determined by KSP. I mean, the last position still fits KSP, yeah, but because you have so much excess, it just approaches your your titrant, right? So you don't really have to do any math or anything if you get far enough in the curve. All right, let's look at pre-equivalence point. So at pre-equivalence point, what are we looking at? Well, they're not going to be equal, are they? No. So what we're going to have is at pre-equivalence point, we're going to have our silver is less than the amount that's required to be equal to our iodide. So at 10 milliliters, this would be 1/5 of the original iodide solution has reacted. So 4/5 of the remaining would still be in the solution. And so iodide would equal 4/5, the fraction remaining, of your original concentration then you have to take into account M1V1 equals M2V2, right? Another way of saying that is you have a volume dilution factor ratio, right? So you take the original volume divided by the diluted volume, right? For our dilution factor. Don't forget this. I'm serious. This is like the #1 mistake people make. Okay? They forget the dilution factor. They forget that they're diluting it when they're adding silver. All right? Okay. And that will give you your molarity here. You can then use the KSP to always solve for the other one, right? Note, we're going to go ahead and make that basic assumption we make on all those ICE problems we did back in Gen Chem 2, because this is a pretty large number compared to our KSP values, right? KSP is 10 to the -15. This is far larger than that. And so we're going to say, well, whatever concentration of iodide we have here, that's going to be the concentration at equilibrium as well. Okay? Our initial concentration is the same at equilibrium. So we're solving for silver, so we put it on one side. That equals KSP divided by the iodide concentration. Everything's to the first power. So our silver concentration is going to be the KSP value, 10 to the -15 here, divided by that concentration we just got. And that will be the silver concentration. Note the silver concentration is very, very small, right? Because almost all the silver gets used up in the reaction. The only silver that is out in the solution is, the stuff that just hasn't hit iodide yet, right? It's just the stuff that keeps getting released from the solid as it dissolves. That's another way of thinking of it. Okay. Again, negative log of would give you 13.4, and note that's that value up here, right? Okay. Anybody have any questions? No? Okay. All right. So let's look at after the equivalence point. What are we looking at for after the equivalence point? Well, after the equivalence point is actually the easiest place to do, right? Because all you have to do is just get rid of the stuff that got you to equivalence point. That's reacted, that's done. That's going to provide, 10 to the -8. We don't care, right? Such a small number, we don't need to bother with it. All we have to look at is, well, we're at 60. What's the excess amount of titrant? So 60 minus 50, which is our equivalence point, right, is going to give us our excess. So we have 10 milliliters of excess titrant. And so we have 10 being added to dilution. That's 85 now, right? So 10 of 85, notice this is just a straight up dilution calculation. M1V1 equals M2V2. So 10 divided by 85 times the original concentration of our silver solution. And that's going to give us our answer. Note that value is much, much larger than the 10 to the -8, right? That the KSP would give us. And so we don't need to bother with any of the KSP stuff. It doesn't make any difference. Okay? Anybody have any questions about that? Okay. Notice that, yes, technically KSP would affect this number, 4 more decimal places down where we don't see it. Okay? And so we go ahead and just get rid of that. We don't need it. We can assume that it's the original concentration diluted. All right, and then we take the negative log of that, and that will give us our PAG. That's 2.23. Again, that's always going to be just how much excess silver did you put in after the equivalence point, right? That's it. That's all we have to worry about. Do you two have any questions about that? No? Okay. I'm going to go ahead and skip this unless you guys need more examples. It's literally exactly what we did in Gen Chem 2, isn't it? With the titration stuff there. Really, this is just making you connect that can be other systems, right? It doesn't have to be an acid base only. You can titrate, with solids. That's fine. The shape of the titration curve. So at the equivalence point, that's going to be the steepest point of the curve. That'll be your inflection point. So if you take the second derivative, you would find that that's 0. Okay? By the way, if you take the first derivative, what happens? That'd be like your peak of your first derivative, right? Because that's the largest change. Yeah, that would be your highest slope, or lowest slope, I should say, since it's negative. But you get the idea. Largest slope magnitude. The sharpness of your equivalence point, the sharper the EP, the less soluble is the precipitant. So if you have a very sharp equivalence point, then that means you're very insoluble. If it's a very low slope, if it has a low magnitude slope, that's a very gradual change here on the equivalence point, then that would be much more soluble. And those are much more difficult to titrate because of that, right? So again, if you took the first derivative, this is going to be your steepest slope, right? This is also going to be your inflection point, so it's also going to be second derivative where it's 0. Okay? Anybody have any questions? No? Did you see the difference here? This is the different KSPs. This is how soluble they are, right? By the way, you can't directly relate KSPs unless they are the same stoichiometry. Okay? So if they're all 1-to-1 ratios, then you can relate KSPs for solubility, right? If they're a 1-to-2 ratio, 1-to-3 ratio, and you're trying to compare it to 1-to-1s and all that, you can't relate KSPs directly. The powers, those coefficients, change how soluble it is versus KSP. Okay? Okay. Any questions? See how that's a much steeper slope there than it is here? The bottom? Yeah? All right, so if a mixture of two ions is titrated, the less soluble precipitate forms first. Anybody surprised by that? Hopefully not. If the solubilities are sufficiently different, the first precipitation will actually nearly complete before the second commences. In fact, if there are large enough differences in solubility, you will precipitate one before you significantly precipitate the other. Consider the addition of silver nitrate to a solution containing potassium iodide and potassium chloride. So you essentially have silver iodide versus silver chloride, right? What's going to precipitate first? Well, the silver iodide, this has a KSP that is smaller, and so you'd expect the silver iodide to precipitate first. The silver chloride will then precipitate second. So you will precipitate a fairly significant portion of silver iodide, and then you will begin precipitating both of them. Okay? That making sense so far? Very good. So when precipitation of iodide is almost complete, the concentration of your silver will abruptly increase. That will cause the silver chloride to begin to precipitate. When chloride is consumed, another abrupt increase in the silver is going to occur. And so yes, you will get what you used to think of as a polyprotic acid curve, right? Where it's like two titration curves stacked on each other. See that? Okay. Are you guys checking this out? And so this is iodide, this is your chloride one. Note that unlike nice polyprotic acids, they don't complete the titration and then go on to the next. okay? In these mixed ion ones, they're going to do the iodide, and then when you're part of the way through the iodide titration curve, it's going to do the chloride one. Because they're not dependent, right? You don't have to have, like, having a chloride, iodide on a silver does not allow you to then do a chloride, right? Whereas the polyprotic acids and bases were dependent. You guys understanding? Okay. Does that make sense? So like a polyprotic acid, you have to have the first proton on before you can get the second one on, right? You don't have a first proton on, whatever proton attaches is the first, right? They're dependent. You have to complete one to get the other. Okay. This is calculating titration curves with the spreadsheet. It's actually a fairly straightforward spreadsheet, honestly. So, again, this is going to be titration of the iodide with Ag, the silver. Here's your KSP. Here's your volume at 0. This is your concentration at 0, what you start with. You're all comfortable with the 0 term, right? That's your initial, what you start with. Okay. Time 0 before anything starts. All right, and this is going to be the concentration of silver at 0, of course. And so then you do the PAG. You always do it in PAG. That makes your life easier. For the silver, right there. This then is going to be the concentration of silver at each of these points in the PAG. Or this way curve. Again, it's just 10 to the negative on doing the negative log, so 10 to the negative power of, right? And then this will be the concentration of iodide at each of these points. Again, you'll use the KSP to get this right. So it'll be KSP divided by your concentration of silver. Gives you your iodide. And then you'll do the volume. And so that right there is your volume at each of those. And you see that you have your 6, which is the concentration right here, or the volume, initial volume right here, times concentration plus the new concentration that you're adding of it. Okay. Does anybody have any questions about any of that so far? Let me know if you guys have trouble with spreadsheets, okay? Just take them step by step. That's the best advice I always can give you on the spreadsheets. The spreadsheets, when looked at totality, seem difficult. When you do them every single cell individually and then bring it down, it's actually very easy. So the endpoints of 2 common argentometric titrations of anions that precipitate with silver, Ag, are actually marked by color changes. In the Volhard titration, excess standard AgNO3 is added to the anion, and the resulting precipitate is then filtered off. Excess silver in the filtrant is then back titrated with standard potassium thiocyanate in the presence of iron. When the Ag plus has been consumed, your thiocyanate ion is going to react with the iron to form a red complex. And notice that's actually that spectroscopy one that you guys likely did in Gen Chem, and you did KSPs originally. It's actually using that reaction. So the thiocyanate makes a complex with the iron that's like a nice red color. And so if you have excess thiocyanate, it'll react with your iron to form a red color. And silver binds it first, and then it goes to the iron. It forms the complex. Anybody have any questions? Okay, so this is used to determine the amount of silver. It often is used in a back titration in order to find the unreacted amount of the silver nitrate in a solution. The Fe3 plus is actually the indicator. It turning into the iron thiocyanate complex is the indication, right? Under acidic conditions, silver thiocyanate will form a solid. Iron thiocyanate will form a red complex. So it'll make your solution red. It's quite a distinct, nice, first starts off as a peach color, then turns into a nice wine red. Okay? And that, of course, is going to signal that you have excess SCN, which tells you your endpoint, which is slightly after your equivalence point, right? It'll be slightly further down on the curve. Okay. Notice again, this is a back titration because what are you doing? Well, you're actually titrating something with the silver, right? And then you end up with excess silver at the end, which you back titrate to find out the actual concentration of what you titrated originally. Is that making sense? Can you see that? Okay. You're good. All right, Fajan's titration, I'm absolutely certain I mispronounced that, by the way. You will have to just look it up yourself at some point to try to get that pronunciation correctly. Good luck, go for it. I am not good at that. This uses an absorption indicator to find the endpoint of a direct titration of anion with the standard silver nitrate. The most common indicator for silver chloride is actually dichlorofluorescein. Excuse me. Apparently I need more water. This dye is a greenish yellow in solution. It turns pink when absorbed onto silver chloride. So in the presence of the silver chloride, it's going to turn pink. Why would you want something like this, by the way? Is a white solid always the easiest thing to see? No, not necessarily, right? And so this can make your titration more accurate. This is one of the things that can make your titration more accurate. The pH of the reaction must be controlled because the indicator is a weak acid and must be present in the anionic form. So should it be acidic or basic? Yeah. If it's a weak acid and you need it in the anionic form, that means you need it in the conjugate base form, right? Okay. The indicator color changes right after the equivalence point when the charged indicator is absorbed onto the positively charged surface of the precipitate. So essentially, this is a way of getting that endpoint closer to the equivalence point, right? By giving you a colored indication of the precipitation. A little bit easier to see pink, right? Okay. Okay, let's go ahead and just finish this slide and then we'll call it a day. Before the EP, before endpoint, your excess Cl. You have excess Cl, and so the fluorescein, denoted by FLUO here, negative, right? Because it's the anion, is going to be floating in solution because you have excess chloride, which is going to build up a negative charge on the surface of that, which will repel it, okay? So what happens when you have excess Ag+, excess silver ion? That's going to start building up a positive charge on the surface. That's going to cause this, the fluorescein, to bind to that surface, changing color to pink. Okay? Everybody okay with that so far? Very good. Excellent. It is like a pink-red depending on how much fluorescein you have. Note if you have a large concentration of indicator, that can materially change the coloring, okay? You probably saw this with phenolphthalein. If you have a low concentration of phenolphthalein, you'll get like a very light pink color you can barely see. If you have a very high concentration, you get more magenta, right? Almost a red. Okay, let's call that it, and we'll start up next time. You all have a great day. Ooh, we have 2 slides left.